So a very famous conjecture, influential conjecture, is the arithmetic quantum uniqueness ergodicity conjecture due to Rubnik and Sarnak. Which studies, if you have a Hecke mass form, it's interested in the distribution of the mass of this form as the eigenvalue goes to infinity. So we fix Q for now. Then you can look at the measure with density given by a Hecke mass new form. So if you have F is let's just say a new form. And then as the eigenvalue of this, so denoted lambda f for the Laplace eigenvalue, as this goes to infinity, the measure here should converge in weak star to the constant measure here. So this is saying that the L2 mass of f, in this sense, is equidistributing with respect to this measure. So this is the quantum uniqueness ergodicity conjecture, and this was famously resolved by Linton-Strauss with key input by Sander Alderman using ergodic methods. So this is a conjecture. So actually, it should also be true in for hyperbolic orbifolds of this kind, which do not come from arithmetic groups. And there are some deep connections to physics and really a beautiful story. But if you are in this arithmetic context, there are some natural variants you can consider. And there is the level aspect. Because now you have many parameters you can vary instead of the Archimedean component, namely the eigenvalue. You can ask what happens if you vary the level. And this, more precisely, there's a conjecture of Kowalski, Michel, and Van der Kamp. It's called level aspect QUE by some people, and some people think one should not use the word QUE here. But anyway, I don't have strong opinions. So just to fix station here. Before we consider the projection, the natural projection over here. Now we take F to be a new form again of level Q. Yes, and then we can look at the same measure as before, and then we can push forward along this map. Now we get a measure on the modular curve of level 1, and this should again equidistribute weak star to the uniform measure here as Q tends to infinity.
That's independently of which you choose for each Q?
Yeah, exactly. And actually, so you can even upgrade this. You can say like this: if you fix Q, it also suffices if the eigenvalue goes to infinity, because then it equidistributes on the level Q thing, and this just covers this even. Yeah. So you can combine the two conjectures like this. Thanks. That's a good question. Okay. So here, there is some partial progress, but I should say it's open in general. The way I stated it here, it's open. But if you replace F by a holomorphic form, one has a similar conjecture, and in this case there's been a lot of progress. So in that case it's actually known. So in this specific setting, it's due to Paul building using a method of Sound and Holowinsky. Let's write it like this. but the method breaks down if you take Hecke mass forms instead of holomorphic forms. In holomorphic case, this, and then it's also known in the depth aspect. So if you take Q to be, you fix a prime, and then you look at the Q be of the special shape P to some large power of n, then there's this whole story which vector you should pick, but at least if you pick the new form as I wrote here, then this is it's actually true and it's provable and it's true. Paul, Nilsson, Pitale, and so. Okay. So that's kind of a bit of background.
Right, but I think we just did the general level like we treated NAQ, right? You're saying for Mars forms?
Yeah, for Mars forms.
Yeah, gotcha.
Yeah, thanks. But what you're saying is in the holomorphic case.
But I'm saying in the holomorphic case, I mean, I think I did it in the square free level case, so maybe.
And then you, okay.
Those three names are also kind of part of the top.
Okay.
Yeah.
That's a good point. Thank you. Okay, but there is actually a conditional proof of this in complete generality, so it's known to follow from subconvexity for certain specific L functions. Subconvexity. So to explain this, the starting point is to use Weil's criterion. So I'm not sure this has been mentioned explicitly, but many of you are probably aware of it. You have to show some weak star conversions like this, right? So you have to prove that if you integrate any compactly supported function against this measure, it converges to this measure. Then it's enough to check it for a sufficient, some basis. And the basis we'll pick here is exactly the basis coming from the spectral theory, namely that consisting of Hecke mass forms and Eisenstein series. Okay, so if we, if f is, so if you take the constant function, then obviously you get 1 on both sides because of some normalization. And if you take, so the case we will look at is if this is a Hecke mass form, Hecke mass, and then you also have to cheat with the Eisenstein part, no, treat it. Then if you evaluate this measure on F and unpackage everything, then you arrive at the inner product between these things of level Q. So this inner product is exactly the one that you can define naturally from this measure. So this is the Weil sum, and on the right-hand side you get, you have to integrate this, it should converge to this inner product, which is 0, because this one is Hecke mass cos form here. So the task is to show that this converges to 0. It's a square here. So this is exactly some trilinear period, which Paul mentioned in the extra time of his lecture, let's say. And this is, when you take the square, there was something with the square root, right? And this is exactly, yes?
You work always in weight 0?
Yes, but you can...
Holomorphic, this doesn't have a weight 0.
No, that's true, but because of the absolute value, this absolute squared always has weight 0.
Oh, okay.
Yeah. So you can also add weight for mass forms, and yeah, but for the time being, let's I'm looking at weight 0. Okay. Yeah, thank you. Okay. So the point is this square here is equal to some L function that Paul mentioned. So there's some large factor, but there's some triple product L function like this. And then there are some local factors that show up, and if you try to evaluate them, if I'm not mistaken, you get some specific exponents like this. So the eigenvalue to the power 1/2 plus something small, and q to the 1. And it turns out that, so if you want to show that this goes to 0 as, let's consider the case where this is fixed and this goes to infinity, then you have to show that this is smaller than q to the 1 minus delta. And this is exactly the subconvex bound for this L function. Yeah. Okay. So Let me write this. You need to substitute Q to the one minus delta, and this is exactly a subappendix exponent. Okay, so just to say that, yeah, but the problem is we don't know this subconvexity bound. This is a major open problem in the fields. So for now, this conjecture, as stated, is open. Okay. So are there any questions?
That's a silly one, but is it important in all of the results you mentioned that you're working on gamma 0? Could you take full level as well?
No, you can do this, yes. So let's see. Yeah, I think so, yeah. Then you would just see the entire non-trivial Niven type, for instance,
Yeah, for
in the
example.
spectral expand, but I think, yeah, it works the same way. That's a great bit. Okay, so this is kind of the state of the art. What I would like to propose, or what me and Rado would like to propose, is not a variation, but a refinement of this level aspect conjecture, of both of these conjectures. So if you recall, we had this Hecke correspondence. Now I just erased it. But we had these two maps. So if you combine the two maps, alpha Q and beta Q, you get a map of the level Q modular curve. It actually is an embedding into the product of the two level 1 guys. And the image is sometimes referred to as the Hecke correspondence. Okay, and if you take the projection to the first component, you get exactly just the map alpha Q, right? But now we can take the measure here, same measure, and then push it forward along this, along the Hecke correspondence. And then the conjecture is that it's still equidistribute. So let me write this out. Conjecture, let's call it conjecture A. That's what it's called in the paper. So again, F here is a new form. On Y naught of Q, and Q is going to infinity. And then again we look at the measure given by mu Q with density F. And now we push forward by this embedding here. Now we get a measure on the product of the two modular curves, and this should again converge in probability to the, in weak star, to the product of the two, to the product of the uniform measure. And so this is exactly what we mean by joint equidistribution. You have two different maps, two ways of, you can also think it like you can push forward by alpha and by beta, and these two are jointly equidistributed in precisely this sense. So obviously this implies this conjecture down here, because you can just take the projection to the first component, right? Okay, so this should be very, very hard, right? Because it's harder than this. Then you can think about why we call it sparse, why it's not a good name, but why did we call it mixing QUE? That's a very hard question. How can we do this? Let me make a few remarks. First of all, so I didn't allow for this, but let's say you put F equal to just 1, right? Then you just take the uniform measure on the level Q guy and push forward by the Hecke correspondence. Then equidistribution is actually easy to prove. So this case just corresponds to the equidistribution of the Hecke correspondence. So so this follows from any bound towards Ramanujan. I don't really know who to attribute this to, the specific theorem. Maybe ranking, I don't know. But this you can actually prove very easily. So somehow the picture that I like to have in mind is as follows. So you have two copies of the modular curve, like this. And then you look at the image of the Hecke correspondence. like this. So this is the image of this level Q guy. And we know that this equidistributes. That's exactly this statement here, right? We know that it. But now we put some, not oscillation, but fluctuation, someone was hoping to say, yes, on the Hecke correspondence. So let me draw it like this. It's always positive. There's some oscillation here. Now the question is, does it still equidistribute when Q goes to infinity? So there is one kind of case which is quite intuitive, because we do know that if you keep Q fixed and let the eigenvalue goes to infinity, so note here there's no condition on the eigenvalue, right? There's no condition. But if you let the eigenvalue go to infinity, you know that by this QUE conjecture, that this measure here should equidistribute on the Hecke correspondence, right? And you also know that the Hecke correspondence equidistributes. So if the eigenvalue goes to infinity very, very fast and Q very slowly, you expect some kind of joint equidistribution. Then this will actually equidistribute. And we'll see how to make this precise later. But the hard part from this perspective, and also in the actual proof, is when the eigenvalue of fx is bounded. Because then it doesn't equidistribute, but still this thing does. Yeah. So that's kind of a good picture to have in mind. Okay. Are there any questions, comments? Okay, so the way we are thinking about this conjecture is really shaped by connections to the so-called mixing conjecture of Michel and Venkatesh. And I think this has received quite a lot of attention recently because Andrew Wiles has some applications and stuff, so maybe it's worth explaining a bit. So they put forward this conjecture. So I'll be a bit quick here. K over Q, let's say, is an imaginary quadratic field. You look at the class group. So ideals divided by principal, fractional ideals. And for every class inside here, you can associate a Higner point. On the modular curve. So it's not very complicated, but it's some, and in terms of the modular interpretation, they correspond to CM elliptic curves. But that means something to you. So this is called the Higner point. And then we define some notion of the size of an ideal class inside here. And this is, by definition, the norm of the minimal norm of an integral ideal. So this is some equivalence class of ideals. So you take one which is integral, and then you look at the minimal norm. Like this. So this is some notion of size. And then the conjecture, we should do it like this. It's a notion of size. Then the conjecture is that if you look at the pair like this inside the product, so you take a B here, which is some class whose norm tends to infinity. Then you look at all the Higner points. So if B is 1, this is a diagonal, and then it of course does not equidistribute. But if you take B with size going to infinity, you get some kind of diagonal, vary A over the entire class group, and this should equidistribute in the obvious sense in the product of these two things. Okay, so there's a very suggestive use of Q here and a Q up there, which we'll unpack now to see that actually there are very much related.
This equidistributes in what limit? As b, qb goes to infinity, or is it?
Sorry. Yeah, Q of B forces the discriminant of K to go to infinity as well.
So you change k also.
Yeah, that's.
Oh, okay.
This implies that. Sorry.
That means for every b, you get a collection according to the class of the appropriate k, and these
Exactly.
sets are the ones that you.
Yeah, and again, if you take the projection just to the first factor, you know, D is forced to go to infinity, so the equidistribution here is exactly a theorem of Duke.
Yeah.
So already here you see that, you know, the mixing conjecture is to Duke's theorem as our conjecture is to Q. That's kind of the thing, but the connection goes even further, I would say, because of this very suggestive notation Q. So this is not a coincidence. So there's actually a Hecke correspondence lying in the background because of the following. One can show that if you look at this pair of hands, I was about to say, pair of points, then you can show that actually this lies on the Hecke correspondence. Let's just call this Q here. And actually this is equal to a point on the Hecke correspondence. So of course this depends on the representative. So what I really mean is that there exists a representative such that this is true. So more precisely, this is the image of a Higner point on the level Q modular curve. And then you take the image of this under the Hecke correspondence. This gives you exactly. Okay, so what is the upshot? Well, you have actually these two problems admit very similar pictures, because again, all of these points, they lie on the level Q Hecke correspondence, like this. And now you have all of these Higner points, which are some point masses on these points. And again, there's a version of Duke's theorem for level Q Higner points. So you know that the points equidistribute on the Hecke correspondence, and the Hecke correspondence equidistributes. And again, it's some kind of joint equidistribution. Yeah, the pictures are very much similar here. So this is and again, you expect some kind of equidistribution in stages. If the discriminant goes to infinity very fast compared to Q, then you expect to have equidistribution. Then it makes sense that you can get equidistribution of the product in this sense, joint equidistribution in this sense. Okay. So now I'll try to explain what we can actually prove. As you maybe should expect, this should be very hard. To prove something unconditionally would be, I think, it's way too hard. So we have some conditional results. And furthermore, we need to restrict to the compacts analog of this. So I'll just quickly review how this works. Why not review, just say the words basically. So you take an indefinite quaternion algebra. Not the split algebra. And then associated to this, you have a compact discriminant D. And then you take a Q that does not divide D. Is cofine to T. And then associated to this data, you hook up a hyperbolic orbifold, which is now compact. This is a compact arithmetic hyperbolic orbifold. And again, we have the natural measure, and we use the same normalization and so on. So here again you have a theory of Hecke operators, and in particular you have a Hecke correspondence. Oh, sorry. Like this. This is again the Hecke correspondence. Basically everything works the same, but you don't have Eisenstein series because it's compact here. So this is kind of a technical condition that yeah. So in this setting, we can actually resolve the conjecture assuming GRH. So I don't know how comfortable you are assuming GRH. That's a matter of taste, but in recent years, starting with the work of sound, there's been a lot of results, developed a lot of methods to go beyond what we can to get new results assuming GRH. And somehow, even the basic case of this conjecture, where you just project to the first factor, is not known. So you need to assume something for sure to get this unconditional without any new major insights. But the main result of the paper is that this conjecture A goes in the I should write this on. Assume then the conjecture holds. In the compact case, when Q is prime. And furthermore, we actually get an effective rate of distribution with effective rate, which is exactly in the same sense as in Min's talk. We get some logarithmic saving, some fractional logarithmic saving. Yeah, so that is the main theorem. And as I said, this is kind of related to other works in equidistribution. So there's a paper of sound who obtained up to epsilon sharp bounds for the Riemann moments of the Riemann zeta function. And his techniques were used firstly by Lester, I'll just write it like this, and Latzevi. So they resolved QUE for half integral weight. Using some of these techniques, I'll come back to what they are more precisely. And then Lohmer, Bromley, and Kayutin, they used similar ideas or related ideas and other input to resolve the mixing conjecture. So I should say that Kayutin has a proof with certain conditions on D. He can resolve this. But removing these conditions, the best result is this paper here, where we resolve it assuming GRH. And then there are some other works, recent work by Yasari, Lester, and Saha, and they consider QUE for the symplectic groups, SP4. More results. Yeah, but that's definitely worth mentioning. Okay, so let's see, 25 minutes. So are there any questions or comments? Yes, go ahead.
Conjecture also for a compact case?
Yes, that's a very good point. They can't do the... This is exactly the compact analog. Yeah, so that's a kind of a fundamental obstruction to deal with the Eisenstein case. Even under GRH, we don't know how to do this. Yeah.
And for the ZA8B that you just erased, it doesn't suffice that decay goes to infinity. You must have Q go to infinity, because otherwise you don't have the images of the Y0Q inside, right?
Yeah, so let's say most extreme case, B is equal to the trivial
Yeah.
thing, then you're just stuck on the diagonal.
Right.
And more generally, if it's bounded, then you're stuck on a...
Kind of union of.
Exactly, yeah. So it is necessary.
Mm-hmm.
Yeah. In our case, it's the same. If Q is fixed and the eigenvalue goes to infinity, you're also stuck on a Hegel correspondence. Yeah, that's a great question. Okay, so in the time that remains, I would like to say something about the proof. I think this circle of ideas, starting with the work of sound, is very interesting and kind of a slightly different flavor. So I would like to explain a bit of that. So the starting point for the proof is again Weil's criterion. Just write like this. So what do we have to test? We have to look at test functions on this product. So you take two Hegel mass forms. Let's just say, yeah, Hegel mass forms. On YB of 1. And then you have to check what this measure amounts to. So you can just give this a name, mu q, suppressing the dependence of f. So if you apply this to this test basis here, and let's assume none of them are constant. So the constant case, if one of them is constant, you're actually reduced to the original equidistribution. Anyway, let's assume they are not constant. Then you can just unpackage what this measure is, and you'll see it's exactly given by integrating this form, the square of f, against f1, and then q f2 over the level q guy here, and q f2 by definition is given by this. Yeah. So these are the so-called Weil sums, which we have to bound in this case because f1 and f2 are not constant. Like this. Okay. And actually, if you look at this expression, it's related to the thing that Paul mentioned in this extra time, which he referred to as the associativity diagram, which has fueled a lot of analytic number theory, and we do the same thing here. So you have 4 forms, and then you can spectrally expand over the embedded diagonal of 2 copies, and then use Parseval. So what you do in practice is just you spectrally expand this guy, and then spectrally expand this guy, and then you pick out the diagonal. So if you do this, you'll get a sum. So this is my notation for the spectral expansion here. And then you curly BQ is a eigenbasis for the spectral eigenbasis for the level Q guy. And then you get here two inner products like this. There's this, you can decompose this. You have the constant function, right? So if you plug in the constant function here, you just get a 1. And here, by playing around with the Hegel correspondence, you just get the Hegel eigenvalue at Q, which you already saw, to the 1/2, and then here you get so these are not the same, this vanishes, so there's some delta function like this. Okay, this is the contribution from the constant term. And then if phi is a new form, then these are exactly the triple products that we already saw. So the square is related to an L function. Okay, so again, we get the square root of some L function. And the same for the other one here. And then there is some sign here, some oscillation. And then there's some local factors. I'll just write them down. You divide by Q, and here you sum over new forms. And then there's some factor coming from the eigenvalue. F. Okay, and then there's also the old forms, but these are small. So let me just write it like this. Okay, but the takeaway is that you get two principal terms, something coming from the constant term, from the constant function, and then some kind of complicated sum of square roots of L functions. Yeah, so this is a bit technical. Yes. In a minute you will kind of see some structure appearing from this slightly complicated spectral expansion. So what do I mean by this? So let's just try to insert bounds. So this, we can insert a bound towards Ramanujan, and you'll get Q to the 7 over 64 minus 1/2. Okay, this is going to 0. And then here, if you insert just Lindelöf, so you expected that these are bounded by Q, the conductor to epsilon. So if you plug that in, then you have a sum over the new forms. There are approximately Q of those. And then you end up with something like this. Yeah. And then the old forms are very small. Okay. So now you see this resonates very well with this picture I emphasized over here, because this part here is going to 0. This is going to 0 as Q goes to infinity. And actually this saving here, this corresponds exactly to the equidistribution of the Hecke correspondence. So this is exactly equidistribution of the Hecke correspondence. Hecke correspondence. And this second term here, well, you see if the eigenvalue is going to infinity much faster than Q, then this is also tending to 0, right? Because you have this minus 1/8. But of course, if this is fixed, let's say it's just of size 2, then you don't get any saving, right? So this tends to 0 if, let's say, the eigenvalue is bigger than Q to some small delta. So this term corresponds exactly to equidistribution on the Hecke correspondence. So this is exactly equidistribution on the Hecke correspondence. Of F. So, yeah, this is at least quite satisfying conceptually for me, because here you see, you do some kind of formal spectral expansion, but then you see that qualitatively, you see exactly the two terms that correspond to this picture I drew over there. You have something equidistributing on the Hecke correspondence, this term, and the Hecke correspondence equidistributing, that's this term. Yeah. Okay, so the upshot is that the conjecture A is true if the eigenvalue is larger than some small power, any small fixed power of delta, assuming GRH, of course. So the hard part is really
under Lindelöf, really.
Yeah, even under Lindelöf, yeah. Yeah, you don't need all of GRH, but it, yeah. So the hard range is, let's say, when this is of bounded size. This corresponds exactly with this intuition I was trying to. So you see, if we just apply absolute values and insert the best possible bounds, if the eigenvalue is bounded, we lose by an epsilon. We lose exactly by this term here. So we have to do something more refined. And this is exactly where GRH comes into the picture. So the idea, which goes back to, I guess that's Ratsfi, but also sound, is that we can't take. So there is, of course, most likely there is a lot of cancellation coming from this sign here. You know, these numbers here will oscillate. We don't have any way of accessing this. So the best thing we can do is just take absolute values. But then the point is that individual bounds, if we just insert individual bounds, doesn't suffice. But we can use that on average. Actually, both of these L functions are a little less than 1. So if they are a little less than 1 and they're kind of independent enough, then you expect that actually such a fractional moment here is also small. That's the basic idea. So I'll just try to yeah, maybe I will not write it down. So I'll maybe just jump directly to the heuristics. Jump here. So I said something about these being a little less than 1 on average, and more precisely, the idea is that if you look at the random variable that associates to each new form, which is this family we're averaging over, mapping to these L functions here. Then this should behave like a two-dimensional Gaussian with a certain mean and a certain variance. So all of this is happening on the scale of log Q. This is log Q mathematics. So one has to be very, very careful. So there's a log Q here, and then it's essentially, there's some, sorry, this is the covariance matrix. So there's two cases. If the two are not equal, two are equal. And then the mean, it's the same. It's again on the scale of log Q. And then the key point is, I said these are less than 1 on average. So the mean is actually, sorry, I forgot here to write the log. So we take the log of these L functions here. So if these behave like, if these things here are a little less than 1 on average, this means that the log is negative, and you can actually see this like this. These two are not equal, and this is. So this is the heuristics.
Sides, both cases are they're not equal. I guess in both sides, one of them should.
So if F1 and F2.
No, both for the covariance and the mean, you wrote two cases, but both cases are not equal.
Thank you. Like this.
And also there, also with the variance. Oh, okay.
So you see there is some structural difference according to whether they're equal or not. So one qualitative thing you can notice is that if they're equal, then the two things are actually they're not independent, right? Because you have ones on the off diagonal. But they are not two dependent because the determinant is not, so it's not degenerate. So there's like considerations like this. But if we believe this heuristic, then it's a small exercise in analysis to calculate this fractional moment. Right? Because what is this fractional moment? 1 over q times this sum over phi of the square root of all of these L functions. This should exactly be the expectation of these two, let's call it x comma y. this 2D Gaussian here. Then this is, you have to exponentiate this and then take the square root. So this is exactly 1/2 of x plus y. And both of these are normally distributed. It's a joint normal distribution, so you can actually just calculate what this is. And in terms of the mean and the variance of x plus y, there's just a closed formula, which is 1/2 times mu plus 1/8 times the variance, like this. Okay, and now you pray to God, close your eyes, and then you plug in the numerics up here. And then this is the fractional moment of truth, and it is actually decaying. So that's very lucky. So you get log q to the minus 1/3/8. Respectively, log q to minus 1/4. If f1 is not equal to f2, and here you get if f1 is equal to f2. Yeah, if you just plug in, you see what the mean and the variance is. So you see you actually do get decay under the heuristics of this sum here. And this is what we want. Okay. So this is a heuristics, but where do all of these numbers come from? Right? I mean, I just claimed this stuff. So now I'll try to explain a random model. So we're getting more and more precise. A random model that explains this heuristics. That's the next step. And then, of course, the final step, which is what is actually in the paper, is making this random model precise or under GRH. So I really won't have time to explain this, but yeah. So what is the overall strategy? We use a spectral approach, look at the Weyl sums, and then we have 4 forms. We spectral expand over the Hecke correspondence, then we single out the constant term, which we can see goes to 0, and then the constant contribution, and then we get some fractional moment of L functions, and then under this heuristic, this should also be small. That's like the overall strategy. Okay. Oh, no, I removed Radu's name. Okay. Let's see. So the basic idea, and okay, we have to touch these L functions. Maybe it's a bit technical for someone's taste. All of this is, but I think it's very interesting. So if you take, let's just look at this case here. Log of this. So the basic assumption, first part of the random model here, is that we assume that this is well approximated by a very short. Assume this is well approximated by a very short Euler product. Now you take the log and then you use Taylor expansion of the log. Then you can rewrite this as some kind of sum of Hecke eigenvalues. So basically this should be p up to x. So this x is some parameter which you should think of as very small, so some small power of q, let's say. We have a sum over all primes up to this. Then we have a first term like this. So this 1/2 is the same as this 1/2. And then when you Taylor expand the log, of the Euler product, you also get a contribution from higher powers. So you get this squared and this to the 3rd power and so on. So you get 1/2 coming from the Taylor expansion of log. And then you have some other terms here. So here, to actually arrive at this, you have to fiddle around with the Sataka parameters and Hecke relations and stuff. But just trust me, you get some expression of this shape. And then you get the higher powers, but they are actually, at least under Ramanujan, absolutely convergent. So you get something small. Yeah. Okay. So this first term, we just keep it as it is. Let me just write p up to x. And then the second term, yeah, so these are like, so now you just open up all the parentheses, and you see you get a minus 1 times minus 1 times minus 1. And then you get all the other cross terms. And all of these other cross terms divided by p. So you get minus 1 over p squared minus up to x. And then you get all of these, some kind of combination of Hecke eigenvalues to the p squared divided by p. And this turns out to be, you can prove that this is essentially log of some holomorphic L functions at s equals to 1. And then plus something small. This thing here is very small, assuming both GRH, but also actually you need the generalized Ramanujan conjecture. But let's just give ourselves everything at this point. Then you can show that this is also small. And what about this? Well, this is a classical result of Mertens. This is minus 1/2 log Q. Okay, and all of this is assuming that F1 is not equal to F2 here. Okay.
X.
What?
X.
X. Yeah, sorry, but X is equal to, yeah, that's a good point. X is equal to Q to this. If you take double log of that, then you just arrive at Q. Yeah, thanks. That's a good point. Plus something small here, meaning of constant size is fine. Okay, minus 1/2. Let's hope I got it right. This is exactly this minus 1/2. And you can imagine if they're equal, then you get minus 1 and so on. So this is exactly the mean that we look for. And why is that exactly? So the kind of, we didn't touch this term yet, right? But the point is, the kind of key point of the random model is that if you look at, so for each p, you can look at the random variable given by lambda phi of p, and then you can let phi vary. And the random model that we would like to, that this heuristic relies on, is that these behave as p is varying as independent, identically distributed random variables. So these are IIDs. And what is the mean and variance? The mean is 0, and the variance, if you try to calculate the variance, you get something 1 over p. So this follows from, you have to average this with respect to phi, so this follows from some application of Kuznetsov formula. Okay, so now you have such a phi here. So if you take this sum that we had before, then it was exactly of this shape. Right, so BP here is just some constant, which is given by the product of these two phi eigenvalues. Okay, and now you sum up a lot of identically distributed random variables. No, identically, it is true, right?
Yeah, it's
Identity. Okay, so the idea is if you sum a lot of these and take more and more of them, then you have something called the central limit theorem, right? That predicts that this should be a normal distribution. So this should converge by the central limit theorem to something of mean. This should be like a normal, Gaussian, with mean given by the sum of the means, which is 0, and variance given by the sum of the variances. So the variance should be exactly the sum. Sum up to x, and then you take b of bp divided by p, right? Which is the variance for each of them. And let's recall what this is. This was exactly or BP squared, of course. BP squared. So let's insert what BP squared is. It's this squared times this squared. Now if you use the Hecke relations again, you'll see that there is some 1s and then some L functions. Sorry, there are some L functions at 1. And essentially here you just get P up to Q, 1 over P, and then plus something small again. So this is if F1 and F2 are not equal, and this is exactly this one here. Yeah. So this is the random model that explains the heuristics. Okay, I didn't say GRH at any point, but the last thing I would like to say is that I'll just state kind of an informal theorem, which is if you assume 3 things, so you need 1, GRH, for all of these L functions. 2, you also need Ramanujan conjecture, and 3, you need some instances of Langland's functoriality. So it's a lot of assumptions, kind of all of number theory. Functoriality of bounded degree, some bounded degree of functions. So something like symmetric 4 power and stuff like this. Then you can recover kind of actually for general families that satisfies this. Then you can recover. The heuristics up to log Q to the epsilon, where Q is the parameter you're varying. Okay, and then as a very last thing, so how do we actually prove our theorem? Because we don't assume these 2 things, right? So this we assume, there's no way around it. Finish off in colorful style. But here we do have the Kim-Sanak bound. And this actually suffices for our sake. So 7 over 64 is less than 1/8. And this inequality is very important for us. So we don't have to assume this, but there's a lot of work. And what about Langland functoriality? Here there's the work of many people, Kim, Shahidi, Ramakrishnan, which proves the cases of functoriality that we need. But actually we push exactly to the limit. So for instance, the functoriality of Sim4, which is due to Kim, is crucial for our applications. So this is why in the end we only need to assume GRH. And where is GRH used? This is exactly the insight of sound, that this approximation is actually provably true if you settle for an upper bound and assume GRH. This is what sound proved. Yeah, okay, and with that I will stop. Thank you.